Therefore, the plant factor is equal to actual energy produced divided by maximum plant rating into T. This is T is that specified time T. This is equation 3. Plant factor is mostly used in generating in generation studies. It is also given as annual plant factor is equal to actual energy generation by maximum plant rating, right, or annual plant factor, that actual annual energy generation or maximum plant rating into 8760. In a year total number of hours is 8760. So, 3 way it can be defined. One is actual energy generation by maximum plant rating or actual annual energy generation by maximum plant rating into 8760. So, this is your equation 5. Next is that your diversity factor. So, it is the ratio of the sum of the individual maximum demand of the various subdivisions or groups or consumers to the maximum demand of the whole system, right. So, what is this? It is ratio of the sum of individual maximum demands of the various subdivisions or groups or consumers to the maximum demand of the whole system. For example, diversity factor, we are using this term FD because demand factor we have used previously the term DF. So, that is why I have made FD. So, there should not be any confusion, right. So, diversity factor with term is FD is given as FD is equal to sum of individual maximum demand by coincident maximum demand, or we can write suppose individual maximum demand, say if P1, P2, P3 like this, if they are the maximum demand for individual consumers, right, the diversity factor FD is equal to sum I is equal to 1 to n, right, Pi divided by Pc. Pi is the maximum demand of load I, right, divide and Pc is equal to coincident maximum demand of group of n loads. So, this is equation 7. So, diversity factor we will use the term FD not DF because demand factor DF earlier we have used, right. So, this is actually your diversity factor. Next is, so these are understandable, right. You have your n number of consumers and for each one you will take, suppose you have n is equal to 3. So, here it should be P1, P2, for example it is like this, suppose you have suppose you have here n is equal to 3, then diversity factor FD will be P1 plus P2, we will take example later on P3 divided by your Pc, right. So, P1, P2, P3 they are individual maximum demand of your what you call that each type of consumers divided by the coincident maximum demand, that is Pc, right. So, P1, P2, P3 the individual maximum demand, right. So, next is the diversity factor can be equal or greater than unity, right. So, from equation 1 the demand factor is DF is equal to maximum, this is from equation 1 we are writing demand factor is equal to maximum demand upon total connected load. Therefore, maximum demand is equal to total connected load into diversity factor demand factor. So, maximum demand is equal to DF total connected load into DF, this is equation 8, right. Now, for ith consumer let us assume total connected load is equal to TCPI, right, and total connected load TCPI and demand factor DFI, this is for ith consumer, right, let us assume this. Therefore, equation 8 can be written as Pi is equal to TCPI into DFI, this is equation 9. So, maximum demand was P1, P2, P3 I was telling just now, right. Suppose for ith consumer it is Pi and total connected load for ith consumer we define TCPI. So, total connected load here TCPI into for the ith consumer the demand factor we can put DFI, this is equation 9, right. So, from equation 7 and 9 you will get that your diversity factor FD is equal to sigma I 1 to n TCPI into DFI upon Pc, this is equation 7. this is equation 7, and here you are substituting this thing, this one you are replacing by your Pi is equal to TCPi into dFi. So, in this equation you are substituting Pi is equal to TCPi into dFi, right, divided by that Pc. So, this is equation 10. So, that is your diversity factor FD. DF is demand factor, but FD is the diversity factor. Next one is the coincidence factor. Coincidence factor, it is the ratio of the maximum coincident total demand of a group of consumers to the sum of the maximum power demands of individual consumers comprising the group both taken at the same point of supply for the same time. Later I will take few example, after that you will see these things are quite easy, right. So, it is the ratio of the maximum coincident total demand of a group of consumers. Of a group of consumers, different type of consumers, maybe commercial, industrial, agricultural, like this, right, to the sum of the maximum power demands of individual consumers comprising the group both taken at the same point of supply for the same time, right. That means the coincident factor we define it is by CF is CF is equal to coincident maximum demand divided by sum of individual maximum demand. So, this is equation 11. So, coincident maximum demand already defined, Pc is the coincident maximum demand, previously we have defined Pc divided by sum of individual maximum demand, this also we have defined, right. So, Cf is equal to Pc divided by sigma I is equal to 1 to np, it is just reciprocal of the your diversity factor, right, because diversity factor FD was sum of sigma Pi your I is equal to 1 to n divided by Pc, and coincidence factor is just opposite, Pc divided by sigma I is equal to 1 to n Pi. This equation is number is 12, right. That means if you see equation 7, just hold on before this, if you see equation 7 here, equations that diversity factor FD is equal to sigma I is equal to 1 to n Pi upon Pc7, and this coincident factor is equal to just reciprocal of it, Pc divided by sigma I is equal to 1 to n Pi. This is 7, this is equation 12. That means FD is equal to 1 upon Cf, or FD into Cf is equal to 1, right. That means from equation, just now I told, from equation 12 and 7 we get Cf is equal to 1 upon Fd. This is equation 13, right. Thus, the coincident factor is a reciprocal of the diversity factor, or diversity factor is a reciprocal of the coincidence factor, right. Now, load diversity. So, it is the difference between the sum of the peaks of two or more individual loads and the peak of the combined load, right. Therefore, load diversity is defined as LD, we are defining load diversity, we define it by LD is equal to sigma I is equal to 1 to n Pi minus Pc, this is equation 14. So, it is the difference between the sum of the peaks of two or more individual loads. Suppose you have three different type of loads are there. So, their peak you are adding, so I is equal to 1 to n Pi, right, and the peak of the combined, your what you call minus the peak of the combined load, that is Pc we have defined earlier, right. So, that is your load diversity, LD is equal to this one minus Pc, this is equation 14, right. So, this is your load diversity. Now, next is contribution factor. It is given in per unit of the individual maximum demand of the ith load. If Ci is the contribution factor of the ith load to the group of maximum demand, that is Ci means suppose it is given in per of the individual maximum demand. Suppose power is 100 kilowatt and Ci is that fraction of it, so maybe 0.4. So, 0.4 is 140 kilowatt, something like this, right. So, if the Ci is the contribution factor of the ith load to the group of maximum demand, then Pc is equal to C1 into P1 plus C2 into P2 up to Cn into Pn. That means PC is equal to I is equal to 1 to n Ci Pi, this equation number is 15, right. So, from equation 12 and 15 you will get equation 12 means this equation, just hold on. So, this is equation 12 Pc upon your sigma I is equal to 1 to n Pi. So, Pc here is I is equal to 1 to n Ci Pi, therefore, Cf is equal to, we are substituting Pc here from equation 12 and 15, I is equal to 1 to n Ci Pi divided by I is equal to 1 to n Pi, right. So, this is actually equation 16, this is your, this is cause your one thing, just there should not be any confusion, just hold on, that just 1 minute. I put this one, this contribution factor, right. So, anyway, so this is your Cf is equal to this one, this is equation 16, right. Now, consider case 1, if say if P1 is equal to P2 is equal to P3 up to Pn is equal to P, say all are equal, right, then Cf is equal to your basically all are P, P1 is equal to P3, all are P, then it will basically P into I is equal to 1 to n Ci, right, P will be cancelled, here also all are P, sum of P, so it will be P into n, because it is P plus P up to nth term, so it will be n into P, P will be cancelled, so Cf will be sigma I is equal to 1 to n Ci, right. The coincident factor in this case is equal to the average contribution factor. So, the average means sum all divided by n. So, this is average contribution factor, right. Similarly, case 2, if C1 is equal to C2 is equal to C3 Cn up to say is equal to C, all are same contribution factor. In this case, Cf will be C into sigma I is equal to 1 to n Pi upon I is equal to 1 to n Pi, right. So, is equal to this term will be cancelled. So, Cf will be is equal to C, that is coincident factor is equal to the contribution factor, right. So, till now we have seen so many terminology, right. Next is load factor. Actually, first we have to see all this, we have to be familiar with all sort of terminology. Then if we take example, I will take few examples, right, then things will be your much clear. So, that is why before putting any example in between, first we have taken this all this terminology, right. Next, load factor. So, it is the ratio of the average load over a designated period of time to the peak load occurring on that period, right. Therefore, load factor we are defining by LF. So, load factor is equal to your average load by peak load, right. So, this is equation 19, or load factor we define average load into T divided by peak load into T, just your this way also we can define, or load factor is equal to this term energy served divided by peak load into T, this is equation 20, either average load by peak load or load factor is equal to energy served divided by peak load into T, this is equation 20. T is equal to time, it may be in days, maybe weeks, months or years, or if T is large, load factor is small, right. For a large T generally you will find that load factor is small. The reason for this is that for the same maximum demand, the energy consumptions cover a larger time period and results in a smaller average load. So, load factor is less than or equal to unity, generally less than 1, right, less than 1. And annual load factor can be defined as, this annual load factor is equal to total annual energy divided by annual peak load into 8760, number of hours in a year is 8760. So, this is equation 21, right. Now, another terminology, that is the loss factor, right. So, meaning is same, load factor, the only thing is that it is the ratio of the average power loss to the peak load power loss during a specified period of time. This is called loss factor, right. For example, therefore, the loss factor is defined as, we defined LLF, loss factor we define as LLF is equal to average power loss divided by power loss at peak load, right. So, this is equation say 22. So, equation 22 is applicable to the copper loss of the system, but not for iron loss. That means, loss factor you can compute is for I square R loss only, but not for iron losses, right. So, only applicable to the I square R loss. Next, we will take one example. For example, so a power station supplies the load as given below. Say time duration is given. For example, say time is hour, say 6 am to 8 am, load is 1.2 megawatt, 8 am to 9 am, load is 2 megawatt, 9 am to 12 noon, it is say 3 megawatt, 12 noon to 2 pm, 1.5 megawatt, and 2 pm to 6 pm, 2.5 megawatt, then 6 pm to 8 pm, 1.8 megawatt, 8 pm to 9 pm, it is 2 megawatt, 9 pm to 11 pm, it is 1 megawatt, 11 pm to 5 am, it is 0.5 megawatt, and 5 am to 6 am, it is 0.8 megawatt. These data are given, a power station as given below. So, that means 24 hours data, that load variations are given to you, right. So, what you have to do is, you have to first thing plot the load curve and find out the load factor. Next is determine the proper number and size of generating units to supply this load. C is find the reserve capacity of the plant and plant factor, and D is find out the operating schedule of the generating units selected. So, these 4 things you have to determine based on the given data. Solutions. First, what you do, you draw the load curve, forget about this line, it is up to this only you think, right. So, first is 6, 10, 6 am, 10 am, this way I have marked, 2 pm, 6 pm, 10 pm, 2 am, 6 am, right. So, at 6 am to 8 am load is 1.2 megawatt. So, at 6 am it is 1.2. So, it will come up to your 6 to 8 am somewhere here. So, up to your it is 1.2 megawatt. Now, 8 am to 9 am 2 megawatt. So, here it has gone to 2 megawatt, and it is 8 to 9 just 1 hour, right. And again 9 am to 12 noon the peak, 9 am to 12 noon if it is going to peak, it is 3 megawatt, right. And then the 12 noon to 2 pm, your 9 am to 12 noon, it is your this thing 12 noon is here, somewhere here is 12 noon, it is 3 megawatt. Then 12 noon to 2 pm 1 point, at 12 noon again it is going down to 1.5 somewhere here, right, and it is up to 2 pm here, right. Again 2 pm to 6 pm 2.5. So, at 2 pm again it is going to 2.5 to 6 pm means up to this 2.5 megawatt. Then 6 pm to 8 pm 1.0. So, it is coming down to 6 pm 1.0, up to 6 it is going, after that coming down, right, 1.080 rather 1.80 to 8 pm somewhere here. Then 8 pm to 9 1 hour, it is 2 megawatt, it is 2 megawatt, and then 9 pm to 11 am 1 megawatt. So, at 9 it is coming down, 9 to 11 it is 1 megawatt, right, and then 11 pm to 5 am, this is 11 pm somewhere here to 5 am, up to this it is 0.5 megawatt, here it is say 0.5 megawatt, and 5 am to 6 am 0.80 megawatt. So, 5 am it is going to 0.8, then 6 am 0.8 is okay, but again it will you have to come here, again it is 6 am is coming. So, finally 1.2 megawatt, this is also, this point is also 1.2 megawatt. So, this way you should complete this your what you call that your load curve. This is called your, you plot the load curve first, right. So, once this load curve is plotted, this is the time and this is the your what you call megawatt load, and peak is of course the your 3 megawatt, right. Once you compute that load curve, then the units generated during 24 hours, right. So, again Again what we will do, that first you calculate units generated in 24 hours. So, in that case that if you see here, just side by side I am trying to put, right. So, 6 am to 8 am 1.2 megawatt, and 6 to 8 means 2 hours. So, 2 into 1.2 plus 2 megawatt load, but 8 to 9 only 1 hour. So, 1 into 2 plus that 9 am to 12 am 12 noon. So, that means 3 hours and 3 megawatt load. So, plus 3 into 3 plus this 12 noon to 2 pm, that means 2 hours, right. So, 2 into 1.5, load is 1.5 megawatt, plus 2 pm to 6 pm, that means 4 hours, load is 2.5. So, 4 into 2.5, then plus 6 pm to 8 pm in 2 hours into 1.8, load is 1.8 megawatt, plus 8 pm to 9, that is 1 hour, 1 into 2 megawatt load into 2, then plus 9 pm to 11, that means 2 hours, load is 1 megawatt. So, 2 into 1 plus your 11 pm to 5 am, that means 6 hours, into load is 0.5 megawatt. So, 6 into 0.5 plus 5 am to 6 am, that is 1 hour, load is 0.8. So, into 0.8, this much of megawatt hour. This way you should compute that units generated during 24 hours, right. Once you have done this, that is equal to total unit generated is 30, after calculating all this, it is 37.8 megawatt hour, right. Now, average load is, just we have seen, no, load factor, units generated by time in hours. So, units generated is 37.8 megawatt hour and divided by 24, because duration from 6 to 6 am to 6 am 24 hours. So, it is your 24 hours. So, that is 1.575 megawatt, that is the average load, right. And load factor is equal to LF is equal to average load by maximum load. So, maximum load is 3 megawatt, maximum is 3 megawatt. So, load factor is equal to 1.575 upon 3, that is equal to 0.525, that is. So, this is the load factor. Now, next is that maximum demand. Next point B, just B is that you have to determine the proper number and size of generating units to supply this load. Listen, we are not doing here any economics, we are not trying to optimize anything, just to have some ideas. So, this point is given, determining the proper number and size of generating units to supply this load. So, from our intuition we will try to make it, but we are not considering any cost benefit analysis or anything, just to give us an idea, right. So, number B is that second point is you have to determine the proper number and size of generating units to supply this load, right. So, in this case that maximum demand is 3 megawatt, right, and that means you have to supply power, this 3 megawatts of power. Therefore, if we choose 4 generating units of rating 1 megawatt each may be selected. Suppose we are taking 4 generating units and each one is having its rating is 1 megawatt, say, right. Therefore, during that period of maximum demand, 3 units can operate, it can will operate, and it has to operate its full load, because 1 megawatt rating, and 1 unit will remain as standby. By chance if 1 unit goes off, another unit may be switched on, right. So, from the reliability purpose 4 generating units considered. If you consider 3 megawatt and 3 units, that is fine, as long as it will generate, there is no loss of generation, but if one generator becomes faulty, then it cannot supply the load. That is why 1 extra is taken, right. So, 4 is taken. So, 3 units will operate and 1 unit will remain as standby, right. Next one is next point is given, find the reserve capacity of the plant and plant factor, right. So, in that case plant capacity is equal to 4 into 1, because we have considered 4 generating units, each one 1 megawatt. So, it is 4 into 1, so 4 megawatt, and reserve capacity will be then maximum demand is 3 megawatt. So, reserve capacity will be 4 minus 3 is equal to 1 megawatt, right. Now, from equation 3, that plant factor is equal to actual energy produced divided by maximum planned rating into T. Now, actual energy, this is from equation 3, right. So, actual energy produced is equal to 37.8 megawatt hour, just now we have seen 37.8 megawatt hour, right, and the plant capacity now 4 megawatt. So, maximum plant rating will be 4 megawatt. So, time duration is 24 hours, therefore, plant factor is equal to 37.8 divided by maximum plant rating is 4 megawatt. So, it is 4 and number of hours is T is equal to 24, time duration 24 hours, because 6 am to 6 am into 4. So, it is coming around 0.39375. For example, if you are chosen instead of 4, 5 your 5 generating units, right, in that case plant capacity should have been 5 megawatt, then reserve capacity should have been 5 minus 3, say 2 megawatt, right. So, in that case this 37.80 divided by 5 into 24, that means this plant factor should have been less than this one, right. So, but anyway, so this is your what you call plant factor is 0.39375, and last one, this number D, last one, that find out the operating schedule of the generating unit selected, right. You have to find out how these units will operate. So, in that case what one can do is, if you see of your own that one generating unit of 1 megawatt must work for 24 hours, because there are nowhere load is 0, minimum is 0.8. If you look at that data, if you look at the data that minimum is 0.5 megawatt, 0.5 megawatt. So, that means this one generator has to be on for 24 hours, because this 0.5 megawatt load has to be supplied, because minimum load is 0.5 megawatt, right. And then second generating unit of 1 megawatt requires 6 am to 9 pm, that 15 hours. If you look carefully, at least 6 am to 9 pm you can observe that load is more than 1 megawatt, that is why 2 units required. If you look at that, your 6 am to 9 pm, say 6 am, if you look at that everywhere 1.2, 2, 3 all these things going on till 2 pm, right, 6 am to 9 pm rather, up to this you see that it is more than 2, right, 2 or more, it is more your what you call 6 am to 9 am, 15 hours. Second generating unit of 1 megawatt is required, because all the time load is 2, so this 2 unit is also required. But if you see third generating unit 1 megawatt, 9 am to 12 noon and 2 pm to 6 pm, 7 hours required, that means it is overlapping. So, this 9 am to 12 noon and 2 pm to 6 pm, for this 7 hours you need all the 3 units should be on, right. So, that means for 1 megawatt 1 unit for 24 hours, then another generating unit must be on 6 am to 9 pm for 15 hours, and third unit 9 am to 12 noon as well as 2 pm to 6 pm 7 hours, because load will be during this duration it will be more than 2 megawatt, right. So, this way from your intuition or from your common sense you can find out how this generator operating schedule can be made, right. So, from the data and from whatever we have made it here, you can have a look and just see this is the way that things can be, operating schedule can be prepared.